Okay. Aldehydes. Ketones. So that's what we were discussing about, right? So with respect to the last class, we were talking about aldehydes and ketones. So hagadre, can any one of you tell me what we had discussed in the last class? Anyone? Yes, good morning. So good morning everyone. So what we had discussed? So we were talking about conversion of aldehydes and ketones to respective alcohol, right? So that's what we have discussed in the last class. So what is that? Conversion of aldehydes and ketones to respective alcohol. Now, can any one of you tell me, if I take an aldehyde, which type of alcohol I am going to expect? Which type of alcohol I can expect? If I have taken aldehyde, which type of alcohol I can expect? Anyone? Yes? Any one of you? If I have taken aldehyde, which type of alcohol I can expect? Okay, yes, very good, Krishna. So this will be a primary alcohol. No doubt it will be a primary alcohol. Fine. So hagadre, which is that reagent we should use? Yes, both of you correct. We are going to get the primary alcohol. So which is that reagent we should use? We have to go with strong reducing agent, right? So we have to go with strong reducing agent or a weak or mild reducing agent, which is required for conversion of aldehyde. Okay, so oxidizing, fine. So which is that reagent? A strong reducing agent or weak? It's not oxidizing, it should be reducing. So which should be that reagent we should use? It's not an oxidation process, it is a reduction process. Yes, we should use the weak reducing agent like sodium borohydride. So which is more than enough to convert aldehydes to respective alcohol. Okay? So yes, it will be a weak reducing agent like sodium borohydride, which can take care for this particular reaction, which will be converting aldehydes to primary alcohol. Okay? So that's where hydrogenation. This is nothing but hydrogenation. Okay? So where hydrogen will be added to the molecules. Same way we have ketones. We have the ketones, which will be converted into an alcohol, as we know. Ketones, always it will give rise to which type of alcohol? Ketones will give rise to which type of alcohol? Aldehydes, they will give primary alcohol. Ketones will give yes, very good. So it will give a secondary alcohol. It's going to form the secondary alcohol. Okay? So once again, an example for hydrogenation. That means reduction, reaction. So hydrogenation, right? So ಹಾಗಾದ್ರೆ strong reducing agent is required. As we know, a strong reducing agent is required. Which is that one? It can be lithium, aluminium hydride. Lithium, aluminium hydride. Okay? So don't think that lithium aluminium hydride cannot catalyze this reaction. No, they can. But sodium borohydride is more than enough. So therefore they will be using sodium borohydride. And for ketones, we have to use lithium aluminum hydride. We cannot use sodium borohydride. Because ketones requires a strong reducing agent to convert into respective alcohol. So that's where we have the reaction. That means conversion of aldehydes and ketones to the respective alcohol. Then what else we have discussed? Can any one of you? What else we have discussed in the last class? So what else we have discussed in the last class? Anyone? And which are very important reactions. That's what I told. Yes, it is Clemenson's reduction and Wolff-Kishner reduction reaction. Okay, it should be Kishner. So first we will go with the Clemenson's. Clemenson reduction reaction. Okay, so that is nothing but reduction only. Why it will be considered as a reduction? What will happen? What is the product here? What will happen to aldehydes and ketones when they will undergo Clemenson reduction? Which is that product? We are going to get Krishna. How it can be? Oh, sorry, Murli. How it can be alcohols? How it can be alcohols? Yes. It's not an alcohol. Which is that product? Yes, very good. It will be hydrocarbons. Yes, it will be hydrocarbons. Okay, so that's where we have the hydrocarbons. So when I am talking about aldehydes or ketones, both can show the reaction with the same conditions. So which is that condition with respect to Clemenson reduction? Which is that condition we have to apply? Which is that reagent we are going to use here? Very important. Which is that reagent we are going to use here? So that is, shall I tell? Or you are going to give the answer? Which is that? Okay, HCl, no doubt, very good. Then what else? Only HCl? Very good, HCl, yes. Then what else we should use? Clemenson reduction, very important one. HCl, yes, of course. Okay. Concentrated HCl, fine. It will be somewhere around 35%. Yes, I was expecting even this answer. Zinc amalgam. HCl, of course. Along with that, we have to use the zinc amalgam. Nowadays, they are using zinc powder also. That is fine. But we will go with whatever is there in your textbook. So that is zinc amalgam and HCl. So that's where there will be formulation of hydrocarbons. Respective hydrocarbons will be formed with respect to Clemenson reduction reaction in the presence of zinc amalgam and HCl. And another product, if you don't write, then also it is fine. Since we are dealing with organic chemistry, So another product will be water. So that's where HCl is going to play the role in removal of the oxygen in the form of water by protonating the oxygen of carbonyl group. Okay, that's where the role of HCl comes into picture. Okay, so this is one reaction where aldehydes and ketones can be converted into respective hydrocarbons. Next one is Wolff-Kishner's reaction. Next one is Wolff-Kishner reaction or reduction reaction. Wolff-Kishner reduction reaction. So naturally here also, okay, already people have given the answer, very good. So in this case aldehydes or ketones, they are treated with NH2. What is the name of that reagent? What is the name of that reagent? NH2. Absolutely correct. Correct answer it is. But I want even name of those reagents. Since I have written the formula, which I appreciate, but along with that I want the name. Which is that reagent? Name of that reagent. Yes, it is hydrazine. Very good. Both of you correct. So that's where NH2. Now, this is nothing but hydrazine. So when aldehydes or ketones treated with hydrazine. So what is that condition we should maintain? Acidic condition or basic condition? What is that condition we should maintain? Naturally there will be formation of a intermediate by the liberation of water. So which is that intermediate? Can you name the molecule? Name of this intermediate? Yes, basic condition. Oh, very good answer. It's a basic condition. By adding, yes, potassium hydroxide or ethylene glycol. Okay? Then what is this name of this intermediate? Whatever I have written here. What is the name of this particular intermediate? Can anyone? Yes, very good Sanjana. It is hydrazone. It's a hydrazone intermediate. Okay? So which on adding potassium hydroxide or ethylene glycol, only this much condition we should maintain or something we have to do? Only this much we have to maintain or something we have to do? So hydrazone, okay, fine. Then we are adding potassium hydroxide and ethylene glycol. Next, yes, we have to maintain the high temperature. So we have to maintain the high temperature. We have to provide the high temperature. So during that time, there will be formation of respective hydrocarbon plus, which is that gas which is getting liberated. Some gaseous molecule which will get liberated, right? Which is that one? Yes, that is nothing but nitrogen gas. So that's what we were discussing in the last class. So when it comes to Clemmensen reduction, reactant can be aldehydes or ketones. Same logic is applicable even for Wolff-Kishner's reaction. And when it comes to Clemmensen and Wolff-Kishner reaction, both are reduction reaction only. Okay? So when I am considering these two reactions, both will give hydrocarbons only. That means what I mean to tell you is, both the reactions, they are involved in the conversion of aldehydes and ketones to their respective hydrocarbons. So what I mean to tell you is, if I consider Clemmensen reduction and Wolff-Kishner reaction, So both are nothing but a reduction reaction. Both are nothing but a reduction reaction. Okay? Okay, I will come to the difference. Very good. So both are with respect to reduction reaction. So what they are doing? Both are converting aldehydes and ketones to their respective hydrocarbons. To their respective hydrocarbons. These are the similarities. So these are the similarities. Then next, when I am talking about the difference, when I was talking about the difference, as you people told, in case of the Clemmensen reaction, we are maintaining the acidic condition, and in case of the Wolff-Kizner reaction, we are maintaining the basic condition. One difference. So what is that next difference? In case of the Clemmensen's reaction, so we have zinc amalgam and HCl, but in case of a Wolff-Kizner reaction, we have the hydrazine. We have the hydrazine and potassium hydroxide. So that's where we have the differences between these two, that is Clemmensen's reaction and Wolff-Kizner reaction. These are the differences between these two. What is that common between them? Based on overall reaction. This is the common thing. These are the difference. Now, another difference here is there will be liberation of gas, that is nitrogen gas, in Wolff-Kizner reaction. In case of Clemmensen reaction, no gaseous molecules will be liberated. Okay? So this is where we have the important reactions related to aldehydes and ketones. So both of these reactions are very important. Fine? So we will move to the next one. Then I was talking about oxidation. I was talking about the oxidation. So what is that oxidation? Oxidation of aldehydes. Oxidation of aldehydes. If I take the first one, that is oxidation of aldehydes. So Hagadre, you should tell me what will happen if I oxidize the aldehydes. What will be the product? If I provide the suitable reagent to the aldehydes, what will happen to the aldehydes? I am talking about oxidation. I am talking about the oxidation. Potassium dichromate, permanganate, okay, chromium trioxide, anything. Yes, it will get converted into carboxylic acid. It will get converted into carboxylic acid. Okay, so that's where we have the oxidation with respect to aldehydes. Okay, but when it comes to ketones, oxidation of ketones. But when it comes to the ketones, R, CO, R. So if I provide the suitable condition, naturally it will be harsh condition compared to aldehydes. It will be harsher condition. That means I have to heat the solution. So now what will happen here? There will be formation of two carboxylic acids. There will be formation of two carboxylic acid, not one as it is in aldehydes. It will be two carboxylic acid. So what is the reason? The reason is very simple. There will be cleavage of either this bond or this bond. That's where we are going to have the mixture of carboxylic acid. When ketones will undergo for oxidation process, we are going to get the mixtures of carboxylic acid. Carboxylic acids. It's not like aldehydes where we are going to get only one carboxylic acid as the product. where we are going to get only one carboxylic acid as the product. But here in ketones we are going to get the mixtures of carboxylic acid. What is the reason? The reason is very simple. In case of the aldehyde group, functional group will be on the terminal. So this is the aldehyde group which is getting oxidized. So the rest of the carbon, hydrocarbons will remain same. Now same logic. But in this case, carbonyl group, that is ketone group, they are present in between the hydrocarbon chain. Ketones, carbonyl group cannot be on the terminal, it should be in between. So therefore, whenever oxidation will happen, it has to give mixture of carboxylic acid by cleavage of the carbonyl carbon, and one of the carbon belongs to any one of the alkyl group. But one of it should be ROOH, right? What is that ROOH? It will be RCOH only. That is because ROOH, okay, I will come to that point. So ROOH is a peroxide, alkyl peroxide. Okay, so it should be RCOOH. Whatever you are telling, it is a peroxide. It cannot be a stable product, it is unstable. Okay, so therefore it should be carboxylic acid. See, for example, I will come to that. See, if I go in detail, now if I take this part, it will be released as, okay, I will take the example itself. CH3, CO, CH3. Oh, okay. In that case, what will happen? I am going to get CH3, COOH plus no carbon will be added. So therefore, HCOOH. So HCOH, because this carbon will be oxidized. Okay. So and this carbon will be oxidized. Whether I am clear? So methanoic acid, acetic acid. If I have taken propanone as the example. If I take CH3, CO, CH2, CH3. So now if I go for oxidation, then I am going to get 2 acetic acid. I am going to get the 2 acetic acid because even this carbon is going to get oxidized. CH3, COOH. So what I mean to tell you is, if I take butanone, if I take butanone, so in that case I am going to get the 2 molecules of acetic acid. No doubt it will be a same molecule. What you have written, the carbon comes extra in the product than the reactant.
So that person's question is, when we have written ketone, you have mentioned only one C. Product 2 C is given. R is
Okay. I will come to that, Sanjana. Here I have not mentioned. It's alkyl group. Whatever one carbon is there, it might be from that R itself. That's what I mean to tell. Okay, it might be confusing. I agree with that. So why I have written another carbon? Because this alkyl group I have not mentioned, which is that alkyl group. So this carboxyl group should be due to oxidation of the hydrocarbon itself. Okay, Sanjana? Okay, fine. Yeah, I agree with that.
So how do you decide that the bond between second and third carbon itself will be?
Mixture, that's what I told. There will be mixture of this one, molecules will be formed. Okay? So that's why we are having the products. All of you got my point? Any doubts? Even methanoic acid can be one of the product. Methanoic acid and propanoic acid. So that's what I mean to tell. Mixture of carboxylic acids will be there. So this is the cleavage, where the cleavage is happening with respect to this particular bond. Acetic acid will be the product. Otherwise, other way around, if this is the bond which is getting cleaved, then methanoic acid and propanoic acid will be formed. So we are going to get the mixture of carboxylic acids. All of you got my point? That is the problem with ketones. So we are not going to have the single carboxylic acid as the product. We are going to have the mixture of carboxylic acid. Okay, any doubts? And that's what, extra carbon will not be there. So try to understand that one. It is a bit confusing. Yes, I agree. So any doubts? So what is that with respect to aldehydes and ketones? When aldehydes will get oxidized, it's going to form the carboxylic acid. Okay, it can provide with mild oxidizing agent also, the product will be there. At the same time, if you are going with ketones, you have to use the strong oxidizing agent compulsory. Along with that, you have to provide the harsh condition, like you have to heat the solution. So now what will happen? There will be a mixture of carboxylic acid. There will be mixture of carboxylic acid. Any doubts with regard to this oxidation? If you have any doubts, you can ask. Okay. So in that case, I will move to the next one. So I will tell this one as very important because you can expect for the board exam, and more than that, it is there for your vivavos, practical examination. Okay. So that is with respect to oxidation of aldehyde. Whatever reaction I am showing, they are specific for aldehydes. This is one of the reaction by using which we can distinguish between aldehydes and ketones. Organic chemistry, functional group, in practical, vivavos will be there. They will ask, we don't know, they may eliminate some of the things, but at present there is no information with respect to practical. Okay? So when it comes to this particular reaction where we are going with mild oxidizing reagent, we are going with the mild oxidizing condition. So naturally, as I told, when we are maintaining the mild oxidizing condition, ketones will not go for oxidation. It will be aldehydes. Okay? So aldehydes are the one, even with mild oxidizing reagent or condition, they will be converted into carboxylic acid. But ketones, no, it's not possible. So that's where we have two major reactions where mild oxidizing condition they will use, and they will utilize this particular reaction for identification for whether a given organic compound is aldehyde or ketones. Because both of them they are having carbonyl group. So if you go with hydrazine and all, both will respond. You cannot distinguish between aldehydes and ketones by using hydrazine or amines, hydroxylamine, whatever it is. You cannot distinguish because both will react. But when it comes to this particular reaction, whatever I will be mentioning, they will be specific for aldehydes. Ketones, they are not going to respond. Whether I am clear? So, one of the reagent which will be used for this particular thing is tolerance reagent. One more question they have asked. What is tolerance reagent? Just one more question. No need to write any reaction. Okay? So what is tolerance reagent? Tolerance reagent is nothing but ammoniacal silver nitrate. Ammoniacal silver nitrate or ammoniated silver nitrate. So that's where we have the tolerance reagent. Some students they will simply write it as silver nitrate. No, it is ammoniacal silver nitrate only. It's a coordination compound. So now silver, that's where silver can go with +1. Okay, so in this coordination compound, silver will be attached with 2 ammonia, a neutral ligand. Ammonia is a neutral neutral ligand. All of you will agree? In coordination compound topic, people have studied. So naturally there will be leftover of +1. There will be leftover of +1. Ammoniacal silver ion. Okay? Now, to neutralize this +1 charge, there will be requirement of a negative charge which will be provided by nitrate. NO3 minus. Hydrogen nitrate, HNO3, nitric acid, HNO3. Right? So same logic, nitrate. That's where we have the ammoniacal silver nitrate. Ammoniacal silver nitrate. So what I mean to tell here is, this ammoniacal silver nitrate under aqueous condition they will be present as ammoniacal silver ion and nitrate ion. They will be present as ammoniacal silver ion and nitrate ion. In reaction, actually this ion, cation is involved in the reaction, not the nitrate. Nitrate is not at all involved in the reaction. It is the silver which is actually involved in the reaction. Got my point? So one mark question you can expect. Name the tolerance reagent, or what is tolerance reagent? No need to write the formula also. No one will expect. If you know it is better. But you should write at least ammoniacal silver nitrate. That word should be there. Or if the symbol is red, that is also fine. All of you got my point? So that's where we have the tolerance reagent. Now this tolerance reagent in the solution, what will be there in aqueous form? It will be present as cation and anion. So that's where coordination compound will come. Okay? When I am talking about tolerance reagent, it will be ammoniacal silver nitrate, means naturally it will be done under alkaline condition. So one of the conditions which will be maintained here is, one is alkaline condition, and they will be using ammoniacal silver nitrate. Okay? As I told, this reaction is specific for aldehydes. This reaction is specific for aldehydes. Now, we have aldehyde, we have to mention, no need to mention general form. We can mention it as RCHO because ketones, they are not going to respond to this reaction. So, aldehydes, when it is treated with ammoniacal silver, because as I told, ammoniacal silver nitrate, when you put it into the water, what will happen? It will be dissociated. So we will take only ammoniacal silver. Twice plus 1. Okay? So that's where we have the aldehydes. When treated with ammoniacal silver, ammoniacal silver reagent. Now they are going to converted into. They are going to be converted into. What will happen? Aldehydes. No. Aldehydes. What will happen? Aldehydes. What will happen? Wow. Anyone? Just before I have explained. A mild oxidizing condition.
Carboxylic acid.
Yes, aldehydes will get converted into. Yes, Sanjana, it will be oxidized. Which is that compound I was asking? Now he gave. Krishna has given the answer. So which is that one? Carboxylic acid. Carboxylic acid. But that carboxylic acid, I will mention it as carboxylate. I will mention it as carboxylate. What is the reason? No. I will mention it as carboxylate. What is the reason? Krishna told, since it is an aqueous condition. That is fine, but not the Perfect answer.
Alkaline.
Yes, that is because due to the alkaline condition, that's what I have told. Tolerance reagent. Okay, because of basic condition. Yes, very good, Sanjana. Okay, so that is because of the alkaline condition. So therefore, whatever carboxylic acid is there, which is getting formed, immediately it will get dissociated as carboxylate. That's what I have written, carboxylate. Okay, now another product will be silver. Another product will be metallic silver. Naturally, when silver is getting separated from ammonia, so what should be remaining? Ammonia should be released. There will be release of ammonia. Since it is a alkaline condition, ammonia will not be present as ammonium. It will remain as ammonia. It will be liberated. Why? Because in acidic condition only ammonia can become ammonium. Since we are providing the basic condition, it will remain as ammonia. Okay? So that's what ammonia will be released. This is the reaction. Now we have to balance the equation. These are the major product which will be formed. But if you go with the reaction, it is nothing but a redox reaction. It is nothing but a redox reaction. Okay? So where? What do you mean by redox reaction? Redox reaction means, as usual, any oxidation or reduction reaction you take, all of them, they should be redox reaction. Where aldehyde carbon is getting oxidized to carboxyl carbon. Okay, and silver ion getting converted into metallic silver. So that's where we have the solid. So it will be metallic silver. So what I mean to tell you is, what is the oxidation state of this carbon? Can any one of you? What is the oxidation state of this particular carbon, aldehyde carbon? If I want to write, I can write like this. Because R is there now. COH. What is the oxidation state of this carbon? Just tell me the value. Oxidation state of this particular carbon. Wow. Fast. Anyone? You told? Okay, Ravikant is telling 2. Krishna told 1. Any other answer? It should be 1. It will be plus 1. That is because carbon, it will not be nothing oxidation because same elements are there. So hydrogen will be plus 1, this will be minus 2. Because carbon is attached to oxygen, so this hydrogen should be plus 1. So by that we can tell that plus 1 is the oxidation state of aldehyde carbon. Now when it comes to the product, this is getting converted into carboxylate. What is the oxidation state of carbon here? Observe it carefully. What is the oxidation state? Krishna has given already answer. Any one of you? Carboxyl carbon, what is the oxidation state? Carboxyl carbon in the sense in the carboxylate form. What is the oxidation state? It will be plus 3. It will be plus 3. Okay? Because minus 1, net charge is there as minus 1. So minus 2 is equal to minus 1. Here no nothing because carbon. So So what I mean to tell you is aldehyde carbon from +1 oxidation state, it is becoming +3 oxidation state. That means aldehyde carbon is getting oxidized. Aldehyde carbon is getting oxidized. So that means when aldehyde is getting oxidized to carboxyl group, another molecule should get reduced, right? So which is that another one? That is silver. So from +1, silver is becoming 0. So from +1, silver it is becoming 0. So that is the reaction we can observe here. So aldehyde carbon from +1 is becoming +3. Itself it is getting oxidized. But in turn it is reducing to some other thing. That means silver ion is getting reduced to metallic silver from +1 to 0. So what I mean to tell you is ammoniacal silver. Listen to me carefully. Ammoniacal silver, in this case it is acting as an oxidizing agent. Ammoniacal silver, in this case it is acting as a oxidizing agent. Why I am telling like this? That is because it is oxidizing the aldehyde group to carboxylate group. So therefore ammoniacal silver is acting as a oxidizing agent. What about aldehyde? Aldehyde is acting as a reducing agent because it is reducing the ammoniacal silver ion to metallic silver. Got my point? So therefore in this case, in this reaction, aldehyde is acting as a reducing agent and ammoniacal silver is acting as a oxidizing agent. Got my point? That's what I mean to tell. A mild oxidizing condition. A mild oxidizing condition they have maintained. Okay, fine. If I want to balance the equation, naturally I should take the help of OH minus because this reaction is carried out under alkaline condition. So I have to take the help of OH minus. Okay? So now +1 -1. It is becoming 0, but on the other side we have the -1. So to avoid that one, first we should balance the number of electrons. So from +1 it is becoming +3. That means it can donate the 2 electrons. That means we require 2 molecules of ammoniacal silver ion which will get converted into 2 molecules of metallic silver. 2 metallic silver, not molecules. Okay? So that's where based on the number of electron we have balanced. So why? Because from +1 it is becoming +3. That means 2 electron it is donating. One aldehyde can donate 2 electron. But one silver can take up only 1 electron. So therefore there is a requirement of 2 silver. So that's what we have written. Now what about ammonia? So what about ammonia? 2 2s are 4. Ammonia should be 4. So 4 ammonia. Okay? Now we can balance the charge. So +1 -1. So if you maintain -1 on both the side, that is be done. Okay? So if that is the case, here +1 is there. How many OH minus I should take? I means 2 + 1 is there. Because 2 molecules. How many OH minus I should take?
3.
I should take the 3 OH minus. Now left hand side also -1, right hand side also -1. So now to balance the hydrogen, I should write respective water molecules on the right hand side. Right? And if I take on the left hand side, it is number of hydrogen will be 3 2 = 6, 12 hydrogen plus 1 hydrogen plus 3 hydrogen. So total 16 hydrogens are there on the left hand side. Now I should add the suitable amount of water to make 16 hydrogen on the right hand side. So 12 is there. So I should be taking 2 molecules of water. Now that's where we have the tolerance reaction. That's where we have the tolerance reaction. Got my point? Any doubts? Even for your competitive exam it will help you out. Okay? Normally for board exam they will ask about tolerance reagent. But for competitive exams it will help you out. So that's why we have the aldehydes which will act as a reducing agent, which will reduce the silver ion to metallic silver, which will be floating on the surface. Therefore it is called as silver mirror test. So due to that reason, since the product will provide mirror appearance, therefore it is called as silver mirror test, which is meant to distinguish between aldehydes and with other functional groups, especially ketones. So therefore, tolerance test or silver mirror test, where they will be using a mild oxidizing agent, that is alkaline ammoniacal silver nitrate. Now, in this case, since aldehyde is acting as a reducing agent, therefore glucose is called as a reducing sugar, because when you take the glucose, even same reaction will happen, because glucose is also having aldehyde group. So due to this reason, because where glucose will reduce the metallic silver ion to metallic silver, therefore it is called as reducing sugar. Glucose is called as reducing sugar. Got my point? But one information, you should not get confused. When it comes to this particular reaction, all the other organic compound where ketones they are not going to respond, only aldehydes they are going to respond. But when it comes to the sugars, listen to me carefully. When it comes to the sugars, don't think that fructose is not going to answer this reaction. No, fructose will answer. Glucose and fructose, both the things can give the reaction with respect to silver mirror test. So we cannot use this test to distinguish between glucose and fructose. No, it cannot be done. Got my point? Because even fructose, it can be answering to tolerance test. That is because of the condition which we are providing, alkaline condition. We will not go in detail, but that thing you should keep it in your mind. But all the other aldehydes and ketones groups, we can distinguish. Okay? So whether I am clear? Any doubts? So that's where we have the tolerance reagent, which is nothing but ammoniacal silver nitrate. Okay? So what will happen? Tolerance reagent will be used to distinguish between aldehydes and ketones. Why? Because whatever reagent we are using, it is specific for aldehydes. It is specific for aldehydes, where silver ion will get converted into metallic silver, which will provide the mirror appearance on the solution. So therefore, it is called as silver mirror test. It is also called as silver mirror test. Okay? Now, when it comes to glucose and fructose, all of us we know that glucose is a aldehyde sugar and fructose is a ketone group containing sugar. Glucose is a aldose and fructose is a ketose. But when it comes to these two sugars, this reagent cannot distinguish between these two, because both will answer this reaction. Okay? That is because of the condition which we are providing, alkaline condition. Due to that, even fructose will respond to this answer, but no other ketones. Any doubts? Any doubt is there with regard to this one? Okay. So next one, once again, specific for aldehydes. Specific for aldehydes. Now when it comes to the aldehydes, another reaction is Fehling test. Another reaction is Fehling's test. Even Fehling's test, it's going to respond to or specific for the aldehydes. Now, for your board exam, 2 marks question can be asked. What is Fehling's reagent A and Fehling's reagent B? It will be for 2 marks. So, Fehling's reagent A and Fehling's reagent B. And while carrying out the reaction, they will mix these 2 reagents. While carrying out this reaction, they will mix these 2 reagents. Got my point? So that's why we have Fehling's reagent A, Fehling's reagent B. So what is that Fehling's reagent? So Fehling's reagent A is nothing but aqueous solution of copper sulfate. It is nothing but aqueous solution of copper sulfate, CuSO4. Copper sulfate, aqueous solution of copper sulfate. What do you mean by that? That is nothing but a copper sulfate dissolved in water. It will give a beautiful sky blue colored solution, very beautiful solution. So that's why we have the aqueous solution of copper sulfate. Naturally, in aqueous solution means copper sulfate, which is a crystal, it will get converted into copper sulfate, which is a crystal, it will get converted into or dissociated into copper ion, that is cupric ion, and sulfate ion. Aqueous copper sulfate means what? Where we are getting cupric ion and sulfate ion. Cu plus 2 is nothing but cupric, not cuprous. Please remember, cupric. Okay, so cuprous means Cu plus 1. So that's where we have the cupric ion and sulfate ion which will be formed. Got my point? That's where we have the reagent A. Now, what is reagent B? So reagent B is nothing but alkaline Rochelle salt solution, or it is nothing but alkaline sodium potassium. Okay, I will write the word only. Alkaline sodium potassium tartarate. Sodium potassium tartarate solution. Okay, alkaline sodium potassium tartarate solution. Here, this alkaline word should come. That's important. What I mean to tell you is Tollens test or Fehling's test. Both are specific for aldehydes and both will be carried out under alkaline condition. So therefore, you have to mention alkaline sodium potassium tartarate. Now this sodium potassium tartarate is also called as Rochelle salt. It is also called as Rochelle salt. Okay, that's where we have the molecule. Okay, so Rochelle salt. Okay, now that's where we have the sodium potassium tartarate, tartaric acid, which is found in the sand. What is that? Tamarind. Yes, it's found in that tartaric acid. So that's why sodium potassium tartarate, where sodium and potassium in interaction with carboxyl group. So structure is not required. So COO minus CHOH, CHOH, COO minus. So that's where sodium potassium. Okay. So that's where we have the tartarate. Fine, sodium potassium tartarate. Got my point? Anyway, we'll continue in the next class. So this is where we have the Fehling's reagent A and Fehling's reagent B. So what is that Fehling's reagent A? Aqueous solution of copper sulfate. What is Fehling's reagent B? Alkaline sodium potassium tartarate. When you are carrying out the reaction, you will mix these two together. They will not be used alone. They have to be mixed together because whatever sodium potassium tartarate is there is going to stabilize the cupric ion in the aqueous condition. The role of sodium potassium tartarate here is they are going to stabilize the cupric ion in the solution. Otherwise, cupric ion is not stable. Stable one is cuprous ion. If you go to their electronic configuration, you will get the answer. Cupric ion is not stable. So therefore, to stabilize those cupric ion, it will be Russian salt which will place the role. So therefore, Fehling's reagent A and Fehling's reagent B has to be mixed together before using. Okay? All of you got my point? Any doubts? Anyway, I will stop here. Okay now? So wish you all happy Christmas. Okay? Thank you. Thank you very much. Take care.